Okay, so next stop, I'm going to go through another types of forecasting model. So first, I want to show you that despite the fact that we are in the machine learning AI, this is one of the areas that I'm going to suggest that you explore the statistical model first, because the statistical model is actually not that bad when it comes to forecasting. Okay, and it's been I think I have some link somewhere. Let me just show you this one, if I can find it, because it just came up to my mind. Probably this one. Okay, sorry, not. Oh, okay, this one. Sorry, I meant this one. Okay. I just sign in. Actually, sorry, I thought it was here, but it's not. Let me find that one for you later on, okay? But I don't want to bore you into this. All right, so the first thing I want you to explore, now we're going to go back to the lecture. So we didn't have much lecture materials, right? You can access the lecture by going to my website and go to the time series lecture if you want to access this information, okay? The first thing you might want to consider when you do forecasting is called exponential smoothings. I'm sure you guys have heard of it, right? It's a forecasting that has a very simple concept, which is the past should influence the future. That's all, right? So if you want to predict the future, why don't you use the value of yourself in the past? That's what the exponential smoothing is, right? So it's the forecasting that using the past observations. But then you know that the immediate past supposed to have more influence to the future rather than the distant past. So then when you are using the exponential smoothing, you have the choice of have the weights that are different depending on how far in the past the data are, and that is and usually the weights are changing exponentially. So that's why it's called exponential smoothing. I guess the word smoothing comes from the fact that usually when you do the weight average of many data in the past, that's the same effects of smoothing. Okay. All right. So these are the equation for exponential smoothing. So as you can see, the data on let me just use my my tablet here. Okay. Okay. So we have the data in the future that we want to predict. It's actually, so at the t+1, right? It depends on the data at the time t minus 1, which is in the past, and also t minus 2, and so on, right? And then, but then you don't use all the data equally. You want to have the weights. So the weights is controlled by the parameter called alpha. And alpha is usually less than 1, right? If it's more than 1, then you have the other effects where the distant paths have more weight. So alpha is supposed to be less than 1. And then the further you are in the past, this term becomes smaller and smaller. So then, and this one means that you have the influence that are exponentially smaller when you use the data that are further in the past. Okay, so and this one actually has the smoothing effects, so that's why it's called the exponential smoothing. All right, so something like that. Okay, and then usually when you have a very simple exponential smoothing, it works fine, right? But actually there are many variations in exponential smoothings, and something that you might want to consider is called the Holt-Winter seasonal method. Because sometimes your data has seasonality. Like if your data is just a trend, that's fine. Usually that's easy. You can use just a simple exponential smoothings. But sometimes you have like dips and throws, and it becomes, you know, like ups and downs and you know, every season. And if you have something like that, then you might want to consider, you know, like a more advanced exponential smoothing methods, right? And this one has seasonality built right into it. There are two variations in terms of your seasonality. One is called additives, and the other one is called multiplicatives. Okay. So without going into much detail, I just want to have you have you get the general idea which one to choose. So if you have the additive seasonality, it's good when the variation are constant through the series. Okay, so you have, you know, like every 12 months something happen at the same time. Like for example, like number of passenger, it always peak during December. So that would be good for like additive seasonality. But when multiplicative is when some things are changing, like the period keeps changing. It depends on, you know, it's more complicated. Then you might want to consider multiplicative. Okay. So this is something I like about statistical models, because you can kind of split your, split your features into like different things, and you can define your parameter that affect just one features of your data, and that's quite powerful. Okay. All right. So I'm gonna let's just use this one in our data, shall we? So that we can have some feel of how it works. Okay. So we're gonna go back to our code, and I'm gonna do S05, which is a stats model, and then C1. Okay. So here you can see that I've actually importing lots of things, and also in order to use this file, you're gonna have to install stats model. I think you guys did it already. So try to run it to see if it runs, to see if the import works. If it doesn't, let me know. Okay, there you go. I have to cross my finger again. Okay, it works for me. Yeah, it takes some. So this library is pretty big. That's why it takes longer to load. Okay, take some time to load. Okay, so and another thing I want to do is I want to load the exponential smoothing model. Okay, so that one's fine. All right, so let's use our good old data load airlines, shall we? And then I'm gonna plot. Oh, and here, well, I mean just. For those who just hear for the first time, I'm just plot it for you so that you can see. Plot series. Okay. So as you can see that this this data has trend. So trend is something that you can see that it kind of goes up. There's a trend component, and also there is seasonality, which means that it kind of repeats itself. And this one repeats itself kind of nicely every 12 months. So you can kind of see that that's the choice that kind of influence the choice of seasonality that I just mentioned. Okay. Okay, so let's do it. First, we're gonna do it real. So we're gonna split the data into the train and the test data. And in here we have to use the one called temporal train test split, because we don't want to split randomly. We have to split so that the train is always in the past and the test is always in the future. Okay? So we're gonna do temporal test train split here. And here I want to do split the y with the test size equal 36. So that means that I'm going to reserve 36 points that are the latest for the testing data. And then everything else goes into the training data. So that's what it is. And then I'm going to keep them into y train and y test. Okay, equal like that. Done. Okay, and if you want to see what it looks like, plot series, right? And then y train and then y test, you can kind of see that the train and test data are split according to time instead of just random, okay, which is kind of important. Okay. All right, so next let's do some exponential smoothing, shall we? Exponential smoothing, that's the long word, all right? Here, let me just kind of show you the documentation too, so that you kind of know what you're looking at. SK time, right? Okay. So here you can see that you can specify a lot of things in here, like for example, trend, damp trend, seasonal, SP, and a lot of things in here. So this exponential smoothing is actually quite nice, because if you can change your model by your parameter. For example, if you don't do season, if you say seasonal become none, then your model becomes just simple exponential smoothings. If you include the seasonal, then it becomes whole winter seasonal model that I just mentioned. So I guess the name kind of, you can kind of choose your like variance of your statistical model by changing all of this. And actually, like the trend itself has two components, trend and then damp trend. So like there's another type of variance of your exponential model that uses the damp trend. So that kind of thing, you kind of have to go into detail in each of the model to see which one is good for you. But I mean, you can also loop through all the model and see which one the best two, and that's something you can do at your disposal. Okay, so why don't we just use the very simple exponential model. So I'm gonna turn the season off. So I guess right now in my code, I have seasonal to be additive, right? But if I just want to have like a simple I guess simple exponential smoothing, like the basic one, I just use none here. And then this one, it actually doesn't really matter, because if the season is none, then SP is called the period. It's no longer valid. It doesn't really matter, right? So that's the thing that I can use. So you can try that too, right? And then I want to do forecasting horizon, right? This is going to be a number between 1 to 37, because I reserve the test data to be 36 points. So FH equal NP.A range. So this is just a way that I can generate this sequential number, that's all. And then I want to make it so that I don't have to hard code anything. So I want to do length of y test and then +1. Okay. So in this way, my forecasting horizon is going to be always reflect according to the number of our test data, because this one is good. So if I print it, then you can see that it's the number from 1 to 37, like that. What? 1 to 36? Yeah, I guess 36. Yeah, 1 to 36. Sorry, 1 to 36. Okay. All right. Next up, I want to do forecast for caster.fit. Okay. I'm going to fit only y train. See this? Because I want to reserve the testing data, right? And then I want to do y predict equal for caster.predict, and I'm going to input the forecasting horizon into it so that I can predict the next 36 points, okay? And then I can do plot series of the whole thing just to see what it looks like, okay? I guess I want to copy this one because this one is too long. Okay, there you go. See, if you only have simple exponential smoothing, it's kind of like averaging things. Like it only do trend, it doesn't do ups and down. So that's probably not something you want, right? You want something that kind of goes ups and down. So, and then if you look at your data, and your data have some seasonality, so let's turn it on, right? That's something you can do pretty easily in this model. So let's do season equal additive. And I choose additive because I know that my season period kind of stay the same. So, right? And then after you do additive, you have to tell the model how much, like what is the length of your period. And this one is 12 months. So I want to do SP equal 12. And see that it's actually not a bad fit at all. You see how powerful this is, right? And you'll see once we go into machine learning model that to produce something like this, it's very hard to do. You got to have lots of data for the model to capture the seasonality. This is very hard. But this kind of thing, you know, you can kind of engineering it out pretty easily from the stats model, because stats model allows you to go into different features of your data like trend and seasonality and adjust it as you wish. Like it's pretty powerful, okay? All right, so and if you want to see the actual like mean square error, then you can use the function called mean absolute percentage error, okay? And let's do that. Okay, there you go. Okay, so this one is 0.05, right? But then if I were to make my model into something worse, which is just a simple exponential smoothing, like that, then I guess my error is bigger. So that's something you can do. And the things that I like about mean absolute percentage error is that when you see this number, you can kind of ballpark it. Like this one is probably like 13% error. So you know like what is the magnitude of it, like how much is it compared to your the original data. So this one is 13%. If I were to use something else, then it's much better. Like this is like 5% error. So this is a good ballparking matrix when you want to compare different models. Okay. So why don't you go crazy? Can you try like multiplicative seasonal? Can you try damp trend? You can try anything. Let's see what happens, right? Get your hands dirty. And again, if you want to look into like the specific details, you kind of have to read the paper. Like each of the model has their own paper that describe things, right? But this one allows you to just go crazy with it, right? So let's try it out to see what happens. Like you can change the SP to see like different seasonal period to see if it works, right? And then try that one out. If you want to see what value you can try, go to this documentation. And for example, I want to see trend. So what kind of trend can I have? I'm just searching for it, right? Like that. And see, trend can be additive and multiplicative too. Okay, so we'll see. We'll see that each of the components, they can be additive and multiplicative, and you do have the choice between each of the features in your data. And then in the meantime, I'll try to find the figure I want to show you first too. Oh, has to be this one.อันนี้รันได้ใช่ไหมครับนั่นเนาะโอเค Okay, maybe I'll just do some of that for you. Okay, I want to change this one into, okay, let me just try something. I don't know, I don't remember this one. I want to do multiplicative, yeah, multiplicative. Okay, I want to, and I think for this one I don't need seasonal anymore. Rerun. There you go. Actually, similar things, actually not that bad. So, pretty cool. If I were to change my seasonal, if I were to guess incorrectly, what happened? See? Even if I do seasonal, oh sorry, this one seasonal is none, right? I don't need that one. I need the first one, this one 6. Yeah. See, if I were to choose my seasonal period to be the incorrect value, now it's kind of, now my, I guess my prediction is quite worse. So, I choose 6. Again, I hope you have some, get your hand a little bit dirty on this, and this is the one that I want to show you. This one is pretty, because every time that I, that I become, that I go to the proposal from the project, I always, everyone always have the feeling that machine learning is better than statistical model, but, and I agree to a certain extent if you are working with a general area, like general type of data, but not forecasting data. Check this one out, okay? So this one is the competition. It's called the AI ML competition. That's this one for forecasting data. So I guess every year, I'm not sure if they still do it now, but in the past, there's the forecasting problem, and everyone try to make the best forecasting prediction using whatever model they can come up with. And statistical model is actually one of the candidates, right? And first, you gotta see the benchmark, right? Do you remember naive model? Because that's what I told you for the first time, right? I told you at the very first of this lecture, because I was telling you that if you were to do the forecasting, why don't you use the naive model first? Because you don't have to do anything, right? Just copy the past data and just paste into the future. That's called the naive model, right? If your model is doing worse than naive model, you just disregard that model. It's trash. And you see that the model, these are the machine learning model. It's actually worse than the naive model. So by spending more computational work, you actually make your prediction worse. Isn't that kind of depressing? You actually spend more time to make your prediction worse. You just copy things to the future. It's actually better in terms of your results, right? And then you see what's actually beating the naive. These are all the statistical model, okay? So this one is the point that I want to show. I want to tell you that when you do forecasting, do the statistical model first, because that's proven in the past that it's actually beating the machine learning model. But then nowadays, if you want to beat statistical model with machine learning, you got to do something even more computationally heavy. So there are a heavy deep learning neural transformer model that actually beats statistical model nowadays. But that one requires lots of computer, which is kind of I don't think you want to try that first, right? When you use the statistical model, the speed is like this, instant. It's instant like that, right? With the same machine, if I were to do the machine learning model, you're going to see that it actually takes some time. And then the results can also be worse than the naive model, right? Here, up. The title? The code? Oh, the code. Okay. Here. Yeah. So when I use the SP equals 6, it's kind of worse because this one the period is 12 months. So if I choose this incorrectly, then sometimes it throw off. But if I were to choose multiplicative, actually it's doing pretty cool. With multiplicative, it means that it kind of finds the season by itself. I don't need to specify it. And if I were to run this, it's actually not that bad, right? So, and you can kind of try this one very easily using this tool, like just change one thing. Sometimes I just do the loop, like try everything and see what happens, right? So I encourage you, strongly encourage all of you to use statistical model first before using machine learning, okay? It will save your life, I'm sure, at some point. Okay, so let's move on. As you might imagine that you have a lot of components and you can change things, right? Why don't we just combine everything into one like unified framework? And people already did. It's called the ETS model. So the ETS model is the generalization of exponential smoothing, okay? And people read it in two ways. Some people read it, ETS stands for error, trend, and seasonal. But some people also read ETS as the, like the name from exponential smoothing. Like I'm seeing both. So I don't know exactly like what the actual, who came up with this, but it seems like there are two ways of, interpreting this ETS abbreviation. That doesn't really matter, right? But what it kind of matters is actually what the what the error, trend, and seasonal means, right? So again, error has two variants, which is additive and multiplicative. Okay, a similar thing. Additive is actually like more simpler version. Multiplicative is more complicated version of modeling the error. Okay, and there is also trend and seasonal. Okay, so if you kind of put things together, it's almost like this, right? ETS model allows you to specify the components, the trend, what do you want the trend to be, what do you want the season to be. It's going to be non-additive and additive. Them, I don't know why it's called them, right? But the season is going to be non-additive and multiplicative, right? And then the combination of this trend and season gives you kind of like the flavor of your ETS model. Okay. So this is what I thought, like in the past, before the ETS model, people came up with different names. For example, simple exponential smoothing, Hall-Winter, there's something called theta model. And each of the model, it's actually kind of like share the same underlying theme, but with different parameter. So I guess somebody just get too annoyed and then just come up with the unified framework that combines everything. So in the ETS model, by choosing all of these components, you can kind of, it's similar, identical to the, like the name that I just mentioned, like simple exponential smoothing, like theta model or Hall-Winter model. It's already included in here. But this one is just a unified framework, okay? And the thing is that we also have this model available in SK-time. So let me show you this one, ETS model, okay? Okay, first, I'm going to do this one. So the nice thing about ETS model is that there's a model called auto ETS. As the name auto, it's called automatics, right? So it's actually just choosing everything for you. So because we already have the unified framework like this, so I guess why don't we just try them all and see which one's the best, right? So that's the reason behind the auto ETS model. And you will see that it's actually quite easy to use, okay? So first, I'm going to do auto ETS, okay? And then I'm going to do auto equal to true. So that means I want this model to actually explore all the variants in here. Just explore everything and just tell me which one's the best. That's kind of, that's something that you would do, right? And since I know that my period is 12, I'm just going to specify it here. But I guess you don't have to, okay? You don't have to, but you can try without, okay? And then n job equal to -1. That means that you want to use all of your CPU cores. Because this one will take some time, so you want to run it in parallel, okay? This one is going to be equal to forecaster, like that, okay? And let's just fit it, forecaster.fit, and then just fit the forecasting horizons into it, okay? And then we just plot the series. That's all. And this one will take some time because behind the scene, the auto ETS actually explore, most all the variants that it can find, I guess, from the page that I show, and then it gives you, I guess, the best results, okay? So, I guess unsurprisingly, it kind of do the job pretty well, right? And if you want to see which one are you using, right? It's kind of, this one is kind of black box, but if you want to see which the variants that you are using, you can use the forecaster.summary. So that will show you what you are actually using inside, okay? So as you can see that this ETS results, right? And then I guess these are the level of things that you are using, okay? So I'm not too technical in the exponential smoothings, but as you can see that if you want to see which one you end up with, so that's kind of the information that you're using, okay? So like ETS, MAN, something like that. That's the variance that you're using with like different coefficient and things like that. But one thing that I can tell you is that how do they pick the best model, the best variance? Actually, the criteria to pick the variance is actually this one, AIC. That one, I actually researched it, right? So this one, let me just show you here. It's called the, I don't know how to pronounce this, akakike. It's probably some Japanese word, right? Information criteria, okay? So when you are judging, like the quality of your model, you don't actually use the mean square error. That's the way with the machine learning, right? In statistics, there's actually a better way. And that's one of the ways. It's called the AIC criteria, okay? And this one is it has something to do with the trade-off between the simplicity of the model and the goodness of the fit. Because once you go into statistical model, you do have a lot of measurements in statistical in order to judge your model. You don't have to do mean square error every time. And that's what this one is doing. It's like the goodness of fit versus the simplicity of the model. So the one that you want is the one with the lowest AIC. So this one has this number, which is, I assume, would be the lowest among all the variants that is tried, okay? So that's how it works, right? So I guess if you're using Python like this library, there is no reason not to use auto ETS, right? Because this one just kind of explore all the variants for you, so that you can use this as the baseline for your result, right? And if you want to go to machine learning, make sure that you can beat this result, right? Okay. Again, I want you to get your hands dirty, so why don't we go to the documentation and see what else can we modify, right? That's always a good learning experience. Okay. So again, you can kind of set the error. So this one will set the search space to be smaller. If you specify the error to be additive, then it kind of it's narrow down some of the search. And you can specify the season. If you want to specify, you don't want season to be additive, just want no season and things like that. So maybe I'll try that. I want to turn off the seasonal in my auto ETS model to see what happens, okay? So I'm going to say season, none. And for that, I probably don't need SP. And let's see what happens. Okay. I think my auto cannot be true anymore if you want to specify things like that. So let me just say that. Yeah, auto has to be false, because if it's true, then it's going to search everything. But if it's false, I think we can kind of narrow down. Seasonal equal to none. Again, it doesn't do it. I don't know why. I have to look into details, but you can try changing things to see what happens. So I'll try it on my own too, just to make sure. Yeah, ignore if auto is equal to true. That's why. Gotta go to false, which is good, right? Interesting. It should have none in here, but it doesn't do that. Maybe I should turn something else off. See, it's actually n and n, which is none and none. That's kind of weird. Like, it's actually choosing the n and n, which is none, but my result is still kind of shows seasonality. So I'm not sure why this one, but yeah, I'll have to dig a little deeper in here. Maybe there's some other parameter that I need to turn off in order to make this happen. Let me see, trend. Can I try trend? But I don't think trend will work, so it's going to be like additive. Yeah, same thing, doesn't, okay. Oh, this one actually failed. Okay, yeah, never mind. Okay, so because the auto one is actually quite auto, so if you want to customize it, you kind of have to play around with it a bit more. But I just want you to get the idea, right, that there are like these tools that you should try firsthand before you dive deep into AI, okay? And last thing that I want to show you is there's something called the theta model. I never use it, but if you want to try, you can try it too. Theta model, where is it? This one here. So this one is the time series that can, that the way that they work is that they decompose the series into 3 things. And then the theta model, it decomposes into like a short-term and long-term components, and then fit them separately and then combine them all together to make the prediction. So this kind of things is available in the statistical model because you can always use like equation and stuff. So let me just show you how theta models is predicting real quick, okay? So maybe I'll just use the one that I have here. So I'm using the theta model. It's called theta forecaster, and all you need to do is just do the seasonal period. And let's see how it works, okay? Okay, so it's performing, I guess, similar, like it can capture the seasons, maybe a little bit worse than the auto EGS, but something to keep in mind that there are many variants of the exponential smoothing that you can do, all right? How are we doing in time? Okay, let me just finish ARIMA and I think we should be able to take some breaks, shall we? Okay. Okay, so next stop is called ARIMA. Okay, so ARIMA is a little, I guess, a more advanced version of forecasting than the exponential smoothing. So this one, ARIMA stands for autoregressive. So that means that it's using the information from the past, right? But then it also has something called the moving average parts that get included in the model. So there is an AR part and then the MA parts, right? Essentially, what the model is doing is actually make the prediction based on the lag value. So the lag value is value of yourself in the past, but then the MA part, the moving average part, is actually modeling the error. So in the exponential smoothing, you're using yourself in the past, the lag value only. But in ARIMA, you're actually using the past value and the error in the past to make the future prediction. So it's a little bit more complicated, I would say. And also, when the model is complicated, then you have more things to set. For example, in ARIMA, you're going to have P, Q, and D. So that's the order, okay? And the order is something that you can kind of determined from the partial correlation plot. So something that I mentioned a long time ago. I probably won't go into that detail, but people actually, you can kind of guess what the right order should be by using the PCF plot. But maybe I'll mention that later. But again, you have to set, what is your order of your AR term, so autoregressive term, and what's the order of your Q, which is the MA, moving average, or the error terms, and also the number of differencing required to make the time series stationary. What I mean by stationary is that it has no trend. It's just kind of flat, okay? Flat meaning that if you have some variation, the variation should not, have some going up or going down. When you have trend in your forecasting data, it's something like this. This one go up, right? If you want to make the trend, if you want to get rid of the trend, what you can do is you can do the differencing of your data. Something that I kind of mentioned right here in C2, if I run it for you one more time. Right here. See, if I have this data, right, this one has trend, right? If I were to do differencing, see this one has no trend. Has no trend meaning it doesn't go up, like the average kind of stay the same. That's called stationary. Okay, so, and you can try that in Python, right? You can just do y.diff. That's all it is, okay? So this is, so how many times do you need to diff your data in order to get the stationary? That's called the D, that's the D value. For example, this one, I would say my D would be equal to 1 because I do one diff and my data seems stationary enough, okay? And then I guess we're here, so then we can kind of see it here too, right? If you want to find the order of your P and Q, you go to here, partial autocorrelation, and you see how much your data is actually above this plot right here. So this one you might want to go to like order of 3 because the rest is actually not important, something like that. I kind of forget all the details, but what I kind of remember is that if you look at this PCF data, then the peaks kind of tells you, what should the order of your P and Qs are. Okay, that's the thing. So that's something you need to kind of specify from analyzing your data. Okay, and then that's for the trend, right? But then if your data has seasonal parts, then you gotta have to do another configuration. And this one, seasonal terms in the ARIMA model is called seasonal ARIMA. And again, you're going to have another extra 3 parameter called the capital P, D, and Q, and then the M, okay? So it's kind of mirroring things together. So P and the capital P is kind of like, it's doing the same thing, but in a different context. So the first one is the trend, and the second one is the season part, okay? So again, as you can see that when the model is more complicated, you have more things to set, and I guess more things to make, I guess, your models run slower, right? But the nice thing about this is that you'll see that there is also something called auto ARIMA that kind of explore everything for you, and you can kind of pick the right one for you automatically. So, all right. So let's see what we can do with ARIMA, shall we? C2.ipynb. Right, for ARIMA, first thing you're going to have to install, I think that we all have this one already. And then, let's see here. There you go. Okay, and then I'm going to import the forecaster called ARIMA, as the name suggests, right? Okay, next up, I'm going to load the airline data, and then I'm going to split the data into train and test. Same thing, 36 points. Okay, I guess I need to run it. Okay. Next up, okay, let's see here. I'm going to type it in to make it slower. So I'm going to do ARIMA, right? And then, okay, first I'm going to do order. Okay, so order equal. So this is going to be P P, Q, and D, similar to this lecture right here. So P, D, and Q, that's the order that you want to input. So this one I try 1 and 0. Okay, you can try other value, right? So I encourage you to try different values too, actually. Okay, and then I want to do C, so now order equal, and then another tuple, which is 0, 1, and 1, and 0, and 0, and 12. So the first three value is P, the capital P, D, and Q. And then the last value is the period, which we know that it's 12 months. So we specify 12s in here. Okay, that's it. That's all you have to do for a RIMA. Okay, and then I'm going to set equal to forecaster. And then same thing, I'm going to do forecaster.fit, right? I'm going to fit with y train. And then I'm going to make prediction, which is predict y predict, right? Equal forecaster dot predict, right? And then I'm going to put y test in it. And then I'm going to do the mean absolute error, right? Percentage error of y test and y predict, symmetric false. I think this one is just so that I don't have to care which side it is. Okay. And I'm just going to plot, right? Yeah, plot series, right? Plot series. And then the whole thing. Okay, let's see what happened. As you can see that it's actually take a little bit longer. There's something wrong in here. Oh, okay. I think my forecasting horizon is maybe wrong. Yeah, I forgot my forecasting horizon, so that's why. Maybe I just copy from here. I need my forecasting horizon. Okay, before I can predict anything. FH equal FH. Okay, let me run again. Got multiple value argument for FH. I don't understand. Oh, okay. When I predict, I don't need y test. I'm sorry. It slipped my mind. No, actually, yeah. Okay, so ARIMA is actually doing quite well, right? If I were to plot the mean percentage error, I feel like this one should be pretty low, like about 4%. I guess that's the lowest. This one even lower than the exponential smoothing model, okay? If you recall, when we used a naive model, we got something around 15%, right? And then by just using like ARIMA, then we were able to do, like pretty nice forecast in terms of, like the mean square error, okay? Okay, again, I want you to keep trying, like try something else. Maybe just change this number to see what happened, right? You can try different seasonal values. You can try different PD and Q just to get your hands dirty, right? Okay, hopefully you try a little bit more, all right? And lastly, for ARIMA, I want to show you this forecaster called Auto ARIMA. So this one, as the name suggests, is auto, meaning that it just try everything for you and just pick the best one. And what I mean by the best one is it's determined by the AIC criteria, not the mean square error, okay? So let me just show you. Let me just copy this one and show you how it works, okay? So I'm loading auto arima, and all I need to do is just kind of saying what the seasonal period is, and then I'll just let it do its thing. That's all. This one is probably going to take a little bit longer, but actually not that long, okay? And now I can even, get the error to be even lower, like it's almost close to 4%, right? And if you want to see the parameter that this model is picking for you, you can do forecaster.getParams, so that you can see what the P and Q and D value is going to be, right? That one. So that's the one that you are using. Okay, I guess to do the text editor, right? So these are the parameters that you're using, okay? Okay, so I guess my suggestion for this is that, if you want to do forecasting, why don't you try, auto ETS and auto ARIMA, like first to see what, kind of establish the baseline for the statistical model, and work from there. Well, it just take 1 second to run anyway, right? There's no reason not to try, okay? All right, so I have another model that I can show you quickly. It's called TBETS, okay? Because, what can you go from ARIMA, right? There are other things that you can, and then this one, it's just simply more things to configure, okay? In TBETS, there are multiple things that you can turn on and off, and that kind of gives you more control, right? So first, it's called the trigonometry seasonality, okay? And there's box cut transformation. This one is a transformation of your data before doing the fitting. And it's been proven to maybe sometimes it's helpful in certain situations. And you can do ARIMA error, trend component, and seasonal component. So, if you want to go into detail, you kind of have to read the paper. But essentially, this one allows you to turn off things that the author thinks that it's useful for fitting different application in forecasting data. And that's all it is, right? And also, there are bets and T-bets, right? And then there are the ways that you can do the seasonal effects in this, okay? This one, probably have to read the paper, but then I just want to show you that in order to implement all of this, it's actually quite easy. Because all you need to do is just import this model right here, bets, right? And the rest the same, because you just do forecaster equal to bets, and then as you can see that this one, it's actually the feature that you can turn on and off. You want to use trend, use box cut, right? Depth trend, ARIMA error, and things like that. So all you have to do is just make this true and false, right? And you can just perform the prediction, right? Let me just show you that. So this one does take some time. So yeah, this one seems a little bit off, and I guess if you want to kind of use this model, you can try fitting around with all of this parameter to see if it helps or not. So this one has pretty high error, okay? And there's also another one called TBET. So this one is using a different seasonality model, and this one is actually quite nice, okay? So, but it's still ARIMA, I guess it's the best so far, okay? There's also another model that has been quite popular, I guess according to my research, it's called Prophets, okay? Prophets is actually developed by Facebook, now Meta, right? And this one is actually, it's pretty cool because it's built with the non-linear trend in mind. So usually the trends are linear when we assuming the trend to be. But this one assuming non-linear trends, right? And it has a seasonal effect. So it's, I guess it's built with the assumption that your data is complicated. So this one has a lot of knobs that you can turn. And I can show you, because I didn't tell you to install this one, so you cannot run the file at the moment. But as you can see, when you set things up, you can actually specify, like seasonality in terms of yearly seasonality, weekly seasonality, and daily seasonality in the same model. And there also, you can take care of your country holidays into the model, Like I can say like my country name is Germany, and then your statistical model is actually aware of the holidays. And so that, because usually when you have like sales data, the holidays also always going to be affected, like they have some strong correlation. So these kind of models actually take into account these kind of external effects into it. So I never play around much with this. It takes some time to run, so that's why I didn't tell you to install this. But if you want to run, you can install Prophets. You can just do this one. I guess I don't have it here, but you can install this model right here. So Prophets, okay, Python, like that. So it's developed by Meta, and you can install it like this. And then, but there's a lot of things you can do. Like it's really complicated, but just want to let you know that such thing, like people go to a great length to develop like statistical model to work with complicated data. So that's another way that you can go. Like if you don't go to machine learning, try model like this, and you can have a lot of knobs to turn to make your prediction useful. Okay. All right. Let's take quick breaks, and we'll come back for the machine learning model, which you guys, I guess, wants to do, right? So see you in a bit.